All right. If your neighbor asked you where you lived, so here is school. There's the school, and your neighbor asked you how far you lived away, and you said, oh, I live about 3 miles away. That's great, because that gives you a nice circle for which to include your location. So you're like, I'm 3 miles away. Cool. So that could be 3 miles that way, 3 miles that way, 3 miles that way, or 3 miles that way. Distance is a scalar. Distance has only a magnitude. So distance is a scalar. It has only magnitude. Scalar. I don't know why it's called a scalar, but it's kind of a cool word. Other things that are scalars, speed. You look down at your speedometer, and it says, you are going 65 miles per hour. Way to go, obeying that speed limit. It doesn't tell you anything but how far you're going. Your computer in your car doesn't know what direction you're going, just how fast you're going. If you want to be more specific, then you can say, I live 3 miles away exactly east. There you go. Okay. Now, that's a vector. If you say, I'm 3 miles east, that's a vector. If you say, I'm 3 miles north, that's a vector. 3 miles west, 3 miles south, those are vectors. If you said, I'm traveling 45 meters per second at 18 degrees, that's a vector. Okay? So vectors have both magnitude and direction. If something has only magnitude, we call it a scalar. If it has magnitude and direction, we call it a vector. We like to draw vectors. We like to draw arrows. And one of the things you find out about the AP when you do the grading is they're really finicky about the arrows. Really finicky. So let me plant a seed for those taking AP Physics next year. If this is your object, and it says you need to draw a vector that's, let's say, 2 meters per second at 0 degrees, this is incorrect. This is correct.
Why?
2 meters per second. It's easier to grade. And as someone who graded about 5,000 tests over the space of 40 hours, you want it to be easy to grade. Yeah. So, yeah, there you go. So, vectors are anchored to a point. This is bad. This is good. Kind of weird, but anyway. So, vectors have magnitude and direction. Okay, now you've all done one-dimensional vector addition, believe it or not. You probably did it about 10 years ago, maybe 8 or 9 years ago. Remember number lines? Where you added things when you first learned about negatives in like 3rd or 4th grade, you first started learning about negatives, and you're like, oh, number lines. Well, that's what you were doing was one-dimensional vector addition. If you take a vector like this, and you add it to a vector like this, in your head you know you have a vector that looks like this. Make sense? All right. And take a vector like this, and then you add it to a vector that looks like that. The resultant should look like that. Make sense? Okay. And then you did number lines. I didn't realize it was going to come up all at once. So let's say that's a positive number, that's a negative number. Add them together. If the positive number is bigger, your result will be positive. Now, if you add numbers to it, let's say that's positive 12. If that's negative 7, your result is positive 5. Okay. So you all did this, remember? Ms. Krabaffel, back in 3rd grade, taught you all this stuff. Should we move on? Some of you are like, no, I have to write everything. You're going to have plenty of time to do vectors. The most important thing, this is why I put it in yellow, when you add vectors, you add them head to tail. You add them head to tail. Do not be, don't fall into the trap of wanting to add them tail to tail. Because if you added a vector, if you add this vector tail to tail, you get a really long vector. But if you add it head to tail, then this is the result. So you add vectors head to tail, then you start where you start and you end where you end. Let me show you what I mean. If you take this vector and put it up here, this vector can be translated right here, and then you start here and you end here, so there's your resultant vector. Okay. You add vectors head to tail, always head to tail. Always, always, always. And then you start where you started and you end where you ended. That's your resultant vector. We're going to do some practices about that. Okay. Similarly, if you move this up, if you translated this one up here, it's going to go like that. And the resultant vector is you start here, you end here, and that is your resultant vector. Right there. Now, you can move vectors around. If you remember your polar coordinates, raise your hand if you remember polar coordinates. Okay, so like 6 of you, yeah, okay. So polar coordinates is when you had the graph, and it was like a series of concentric circles. And instead of using x and y, you had r and theta, I think. Do these two use r and theta? Okay, some value in theta, where r is the length of the vector, and then theta is the angle from 0.
Oh boy.
Yeah, definitely don't remember that.
Oh. Okay, well, this will be fun when you actually get to the point. Polar coordinates are a little bit different than Cartesian coordinates. So Cartesian coordinates you've recognized are,
It's the graph.
yeah, you recognize this? There's x, negative x, and there's y and negative y. And this is coordinate 1, or quadrant 1, 2, 3, 4.
Yeah.
So this is called Cartesian coordinates. Well, polar coordinates are a little bit different. Polar coordinates, they usually draw a series of concentric circles around the origin. And polar coordinates are used to tell you you have a vector originating at this point. It's this many degrees off the origin, and it's this long. So if you take a vector, and you're like, I'm going to make a vector, and the vector is right there. So far, so good? Well, in Cartesian coordinates, you go, all right, I got plus 4 on the x, and plus 8 on the y. So this point right here has the coordinate of 4, 8. That's familiar, right? Cartesian coordinates? Well, what polar coordinates do is they say, okay, what we care about is not the legs, but the hypotenuse of this right triangle. So we care about the angle theta inside that hypotenuse, and then we care about the hypotenuse.
Oh gosh.
Here's the cool thing. To go from the polar coordinates to the Cartesian coordinates, you just use trigonometry. And to go from the Cartesian coordinates to the polar coordinates, you use the Pythagorean theorem. You remember the Pythagorean theorem?
Yes.
A squared plus b squared equals c squared. Okay. So if you want the, I'm going to go ahead and label this r. If you want the, actually let's label it h for hypotenuse. If you want the length of the h, you know the length of the h is the square root of the x squared plus the y squared. Right? The length of the hypotenuse, that's the c, is the square root of the 2 legs squared. Okay. And if you want theta, theta is just the tangent of the y over the x. Because theta is opposite over adjacent. We call that?
Yeah.
Okay. So that's how you go from polar coordinates to Cartesian coordinates. Now you're going to be that much better when you get to your math class. You're like, oh, we already did this in physics. Okay, so we'll come back to that in just a little bit. I just wanted to plant a seed because we're going to use that a lot. Okay, any questions about that nonsense or this nonsense? All right, move on. So, two-dimensional vectors. Now this is why we're here. If everything was one-dimensional, we wouldn't even have to do this unit. But in reality, things are rarely just existing in the x or the y or the z. We'll do 3 dimensions when we do magnetism. But until we get to magnetism, until we get to May, everything is x and y. So anyway, two-dimensional vectors. You can also add vectors that are not lined up in the x-coordinate by adding them head to tail. So add that vector to that vector, the resultant vector still starts where you start and ends where you end. Okay. So notice the vectors were not changed in magnitude or angle. They were only translated parallel to themselves. So you can move the vectors around, and the resultant vector still starts where you start and ends where you end. if you are adding them head to tail. Notice, the vectors were not rotated, and the vectors were not stretched. If you change the magnitude of the vector, you change the vector. If you change the angle of the vector, you change the vector. Somebody says, I live 3 miles away, 0 degrees to the origin, you're going to find the house. If you go 3 miles away at 45 degrees to the origin, you're going to find the wrong house. Is Johnny here? There's no Johnny here, go away. You obviously did not translate that vector parallel to itself. You changed the angle, that changes the vector. Okay, want to see another one? Okay, so this little vector and this little vector, put them head to tail, results in that vector. So you got this little vector and this little vector, you move them head to tail, and you have this resulting vector. Okay, now here's one for you to do. I hope only one. I don't know, I played with the animation earlier today. So, all right, so those two vectors. Scribble those vectors on your page, head to tail, and see if you can come up with a resulting vector. And when you have your resulting vector, show it to a neighbor. By the way, if you have colored pencils, I find using different colors to help quite a bit when you're doing vectors. So you make each vector a different color, and then make the result in the third color. If you want colored pencils, they're over the microwave. I find colored pencils to be kind of handy, or pens and pencils. But if you don't want that, that's fine. I just thought I just like doing that, so you can do that too. So once you've got your two vectors, show it to your neighbor and see if your resultant vector looks similar to their resultant vector. Okay, so this is what mine was. I took that vector, and I added it to the tail of that vector, and I got a vector that looked kind of like that.
Oh.
You get something like that? Okay.
How do you know which way to point?
It doesn't matter. So as long as you start where you start and end where you end, start at the butt of the first vector and add at the end at the head of the next vector. As long as you start where you start and end where you end, you'll always get the same vector. In fact, if you chose to put this vector right here, let's say you're going to move, instead of using this vector here, you're going to put it right here, your result is still going to be the same vector.
I know, but I'm talking about like the green arrow.
Mm-hmm.
What if it was facing like this? Like down. I'm sorry. That doesn't make sense.
Then you probably started at the end at the wrong side. So as long as you start at the beginning of the first vector and end at the tip of the last vector, then you'll get that vector will be properly aligned.
How do you know which vector is the first or?
It doesn't matter. It doesn't matter in what order you put them. Kind of like if you wanted to go right here, that's your resultant. You can go this way, then this way, or you can go this way, then this way. You're going to get it the same way. Or you can go this way, then this way. So it doesn't really matter if you in what order you add vectors, as long as you add them head to tail, your result will always be the same. Let's do another one. Again, scribble these in, and then show your neighbor and see if you two agree on a resultant vector. what direction, with the show of your hand, up, down, left, right, what direction is the resultant vector? Okay, good. If you added them head to tail, the resultant vector should have been mostly up-ish. Something like that. Now, if you added them tail to tail or head to head, then you could get a horizontal vector, and that is wrong. So if you add them head to tail, your resultant vector should be a more or less vertical vector. Questions? When? No, it can't go down, because regardless of the order, if you start here, end here, if this one's put up here, you'll start here and end here. If this one's put up here, you'll start here and end here. So regardless of the order at which you add them, as long as you add them head to tail, your first vector is going to start down here where you started and end up here where you ended. Other questions? Then off we go. You don't need to write anything down here, it's just kind of fun. So you can do this with 1, 2, 3, 4, 5, 6, doesn't matter how many vectors you have. So take a look at this mess, don't write anything down, just take a look. See if you can predict in your head what the, where the resultant vector is going to be. These 4 vectors, which are obviously improperly placed, because they're all butt to butt, see if you can figure out where the resultant vector would be. That way?
Yeah.
Yes. Exactly right. Because this and this would form a vector that exactly cancels this, right? So imagine this is a leg of a right triangle. This is a leg of a right triangle. Move this leg over here. You're going to get a line, a hypotenuse is like that. That vector is going to cancel that vector, and that's going to be the vector that's left over. So, and it doesn't even matter what direction or what order you place them. When you place them all over the place, like here, I placed them in an odd order, the result is still that direction. Isn't that fun? Yeah.
I don't understand what you mean by canceling vectors.
If you have a vector, say we have this vector, so I move this vector over, this vector is going to come down, the resultant is going to be like that. Now, I don't add vectors tail to tail, I add them head to head. So I'm going to move this vector over here, and you're going to have a vector that looks like that. So by adding head to tail, this vector gets canceled out by this vector. Kind of like if you, on a number line, if you had +5 and you had a -5, they cancel out to 0.
Yeah, okay.
So that's what's going on. So when all is said and done, these 2 vectors create a vector that exactly opposites that one. Those 2 vectors cancel out, and this is all the one you have left.
Doesn't make sense to me.
So, if you have more than like 2 vectors and you're trying to find the resultant, you just have to place them head to tail, and you'll always still get right. Okay.
Regardless of the order. I could have gone over here and gone with a different order. It would have been like this, and it'd still end up like this. Okay. Questions before we move on? Moving on. Okay. Hey, here's that. Hey, look, trigonometry. This is actually kind of cool. There's like cosine, cosecant, cotangent, sine, opposite sine, all this fun stuff. Yeah, this is a fun little graph, or fun little animation I found. So now, resolving vectors into their components, this is where the math comes in. Because again, a vector is a hypotenuse of a right triangle. So let's look at this vector. Couldn't be simpler. 45-degree angle, bada bing. And we can even make it really, really simple. We could say, oh, okay, so it's got an x component and a y component. To determine its x and y components, we just use some triangle math. Or triangle measurement. You remember triangle measurement?
Yeah.
Trigonometry? Okay. So if we say the magnitude is m, the vector of magnitude is m, then what formula might we use to determine what the x and the y values are? So let's start with the y value. This y value right here. Y equals what? What formula might we use? M. So yeah, definitely if m gets bigger, y should definitely get bigger. So m should be in there. What else? I'll give you a hint. Your options are sine, cosine, and tangent. Tangent. Tangent is op over adjacent. Is M opposite over is M either opposite or adjacent? No, it is a hypotenuse.
Oh, M is.
M is the hypotenuse.
M is a hypotenuse. So sine is opposite or adjacent?
Opposite.
Opposite. Sine is opposite, and that leaves adjacent for cosine. So, looking at this angle, we're using the hypotenuse, and are we using the opposite leg or the adjacent leg?
Opposite.
Opposite. So, to get y, it's m sine theta. And I'll show you how that cancels out here in a second. M sine theta. To get x, you probably figured it out. X is what? M cosine theta. Okay. Now I'm going to derive them for you to prove that that actually is the case.
Sorry.
So there you go. So if you want the x component of a vector, it's just m cosine theta. If you want the y component of the vector, it's m sine theta. Prove it. Okay, I'll prove it. M is a hypotenuse, right? Hypotenuse of the right triangle. Okay. Cosine is adjacent. Cosine of theta. Sorry, cosine of theta is adjacent over hypotenuse. Canceling these two out, you get adjacent. X is adjacent to the angle theta. Make sense?
Yes.
And the same thing here. M is the hypotenuse. Sine over theta is opposite over hypotenuse. Canceling out the hypotenuse, this is opposite. And y is opposite the angle. So we call this resolving a vector into its components. So if you say, if you have a helicopter, you can fly to my house, which is right here, in one way. But you don't have a helicopter. You got to go down 3rd Street and then turn on Trump Street. Anyway, so you have to drive that way because you have a car. You don't have a helicopter. So, but your end result is the same. The distance or the displacement from where you started to where you ended is the same. Okay, questions? You ready to do a few?
Yes.
I'm going to give you 3 vectors. I'd like you to resolve these vectors into their components. The first one has a magnitude of 10 units at an angle of 15 degrees to the origin. Vector 2, 6 units at 80 degrees. Vector 3, 5 units at 200 degrees. So go ahead and resolve those into their components. Can I erase this? Okay. I'm going to make a little table so we can collect all of our information. This I'm going to keep up here for a little bit. I'm also going to turn the light on so you can see my board. You can see the projector just fine. So. When you're doing this, please make sure your calculator is in degrees. We don't use radians unless we're talking about rotational motion, and we're not going to do that until physics AP.
Well, I'm not getting errors, so
Yeah, when you get it, take a look. It's like, does your x and y, imagining slapping that vector down on a Cartesian coordinate, does that look like where your x and y is? So take a look at that and say, that makes sense to me.